Right, hi again. So, what I wanted to do today is start with a 3043, which is on the thermochemistry. Have you started this booklet yet? Right, I'm just waiting for you to type. No, okay, no, that's great. Okay, so what we're going to do is revise entropy again, that we did last time, because it's been a while since you've seen it, and enthalpy, because that's a new term. You did meet it at level 2, but let's just revise it for level 3. Then we're going to look at a lot of definitions which you need to know and be able to use, and then we'll look at some calculations using calorimetry and heating curves. So let's get going. First of all, types of energy. Now, in chemistry, there are 3 main types of energy. Which are the ones you can think of? So I know you're typing, right, the chemical energy and its chemical potential. So it's the energy involved in the bonds. So that's the chemical potential energy. Then there's also, of course, the particles are moving around, and that's the kinetic energy. And yes, correct, the last one is the heat energy. There are obviously other energies, but those are the 3 main ones we're going to deal with. So the energy in the bonds, which is the chemical potential energy, the heat energy, which is the word we use enthalpy for. So when we use enthalpy, it means heat energy, and then kinetic energy. So there they are. So for instance, water molecules that in the gaseous state have got more energy than water molecules bound up in ice, because they're moving around faster. So that's the kinetic energy. They've got more kinetic energy. Potential energy, that's that energy bound up in the bonds. And then of course the heat energy. We can either add heat to the, to water to make it melt, to go into a liquid and so on, or heat can be given off when that potential energy bound up in the bonds gets released. Okay, so there are 2 different types of reactions. Now that writing is a bit small, so I don't know if you can actually see it, but the one where you've got arrows point going outwards, that's when it's hotter in the reaction and heat is being given out, and that's an exothermic reaction, compared to the other one where it's colder in the reaction, so heat is being drawn from the surroundings into the reaction. So you should have met them last year, an exothermic reaction and an endothermic reaction. So that type where the heat is being given off or taken up is what we call an enthalpy change. How much heat was given off, how much heat was taken up. So that is what we mean by delta H, H for heat, and the delta is the change. And we can work it out by saying, what is the final heat, so the heat of the products, and compared it to the heat that we started off with, the heat of the reactants. So your delta H is the heat of the product, subtract the heat of the reactions. So it's the heat absorbed or released. So there are your reaction diagrams where we show the energy. And on the one on the left, if the energy of the reactants is higher than the energy of the products, has energy been given off or has energy been taken up? It's been released, correct. So reactants had more energy, now it's turned into products, so the energy has to go somewhere, so it's been given off. And that's what we call the exothermic reaction. Now, if you look at that equation, if delta H is equal to H products subtract H reactants, we're saying a smaller number subtract a bigger number, because obviously this is a smaller number compared to the bigger number, you're going to land up with a negative number. So if I said 2 subtract 8, I'm going to get negative 6. So that's what I mean by that. So an exothermic reaction will always have a negative delta H, and obviously an endothermic will be the opposite. So that is going to have a positive delta H, because if this was, for instance, 8 up there, and I subtract the reactants of, say, 2, I'm going to get 8 subtract 2 is a positive 6. So that's something you do need to know. Now let's compare enthalpy with entropy that we did last time. So remember, entropy is a measure of the dispersal of the energy. So it's not the heat energy itself, but how that heat energy is being dispersed. Any energy, but it's I could either have it dispersed by lots of particles, all carrying a small amount of energy, or I could have it dispersed by fewer particles but having big chunks of energy. So if there's a big temperature change, so like lots of energy being released, it's going to affect my entropy a lot. Or if I've got lots of molecules all being affected, then that's also going to affect my entropy a lot. So that's what we're saying. The more particles in the system, the more energy can be dispersed. The more energy those particles have, so if they've got a high temperature, the more the energy can be dispersed. So I could have like one molecule, but if it's carrying a lot of energy, you can zoom away and disperse that energy. And then obviously gaseous have got more kinetic energy than a liquid or a solid. So they're going to have more entropy because they're dispersing more energy as they move around. And you can think of it as disorder, because if you've got lots of gaseous particles moving around, it's all going to be mixed up and disordered and chaotic. So it's an easy way of trying to visualize entropy. If there's lots of disorder, then there's lots of entropy. And we had that sort of very ordered solid compared to slightly more disordered liquid compared to the much more disordered gas. So if you think of these gas particles, they're zooming around, so they're transferring a lot of energy everywhere. So there's a lot of dispersion of energy here. Here they're not moving around as much, so there's less energy involved, so there's less entropy because it's less dispersal in this one over here. And there, of course, it's very ordered. They're just vibrating, and so there's not much dispersal of energy in this solid form. So one final point on entropy, it's a slide we saw last time, is that for a reaction to occur, remember that delta S must be positive, the overall delta S. So that's from Newton's second law of thermodynamics. Everything has to tend to chaos, otherwise it's not going to happen. And so we do have to look at the system and the surrounding. So for instance, what I've got here is your hot cup of coffee or hot cup of Milo or whatever you drink, something that's hot, that's got a high temperature. So the particles in here have got lots of kinetic energy, so they're zooming around, and so there's going to be high entropy in this hot cup of coffee. In the surroundings, there's a low temperature, but there's lots of particles in the surroundings, but they're moving around perhaps more slowly, and so there's perhaps less entropy. I mean, I'm not thinking about one's a liquid, one's a gas. I'm just looking at the sort of general overall picture of what's happening. Now, when this cup of coffee cools down, as the particles cool down in the coffee, they're slowing down. What do you think is going to happen to the entropy? Are the particles going to have less entropy? Will there be less chaos or more chaos? Yes, there'll be less entropy, correct. So the entropy decreases in the system, the coffee cup, but what happens in the surroundings? So in other words, you've got to think about what's happening to that heat, where is it going and what's it doing? So I can see you're typing. But I know that's quite a long sentence. So that heat is being moved to the particles in the surroundings, so they're picking up speed, they're picking up kinetic energy, so they're starting to zoom around, so there's going to be more disorder in the system. There'll be a greater entropy in the system. So because you've got more entropy happening in the system than what is more entropy occurring in the surroundings than what is decreasing in the system, your coffee cup is going to cool down. That reaction is going to happen where it cools down. So we've looked at enthalpy, we've looked at entropy, and now we're going to see how they're related. So are those two ideas though clear? You've got enthalpy as a heat energy. So we're looking at how so how the energy is bound up in those bonds, but when a reaction happens, that energy either must be given off as heat energy or it has to be taken up if the bonds are going to be stronger, say for instance, in the products. So energy has to be taken up. And then we've got that dispersal of energy. And here I've just got here, by the way, what I said about the entropy of the surroundings increasing, entropy of the system decreasing. So here we're going to compare them. First of all, I'm just stating again, delta S has to be positive overall. Otherwise, the reaction will not happen. And we've got to now compare enthalpy and entropy. In the booklets, I have given you a mathematical equation, but you don't have to have it for the exams at all. You would be using it for university. Have you come across Gibbs free energy at university? Yes. Okay. And to me, it's actually easier explaining it through a mathematical equation, but that's just me. Yeah, that's right. Okay. So, or there's even a simpler one, but that is one of them. So, if I'm trying to relate enthalpy with entropy, remember a drop in the temperature decreases the kinetic energy. So if I'm having for instance, an endothermic reaction, energy is being, the temperature is dropping because it's trying to suck in energy from the outside. So drop in temperature decreases the kinetic energy of the system. And so if the kinetic energy is decreasing, the disorder is going to decrease in the system and the entropy is going to decrease. Is that sort of clear? So in our system, everything's cooling down, everything's slowing down, there's going to be more order. So I'm going to have a positive delta H because my the temperature is dropping, and I'm also going to have a positive entropy for that system. I could also have the other way, where a temperature is increasing, and so I've got more kinetic energy, they're moving around faster, and if they're moving around faster, there's more disorder, and so there's also more entropy. Now, with these, and as I say, you've got to do this for systems and surroundings, because if you just look at the system, then you might say a reaction is not going to work, like your coffee cup. You know, you can't have increasing order by itself, because we know by Newton's law of second law of thermodynamics it shouldn't happen. So you have to look at that and the outside. And what we do is we come up with these 4 different types of combinations where we take our enthalpy and entropy and say, will a reaction happen if I have either an endothermic reaction, exothermic reaction, and a positive or a negative delta S entropy. So this comes from your booklet. Just notice, by the way, in the booklet, that last diagram is incorrect. So I think it's around about page of 7 or so in the 3043 booklet. One of these symbols are incorrect. It is correct here. So let's take the first diagram. Do you think that's an exothermic reaction or an endothermic? If you like to match. It's exothermic. You can see heat's being given off. So delta H, remember what we said, if for an exothermic reaction, delta H is negative because the products have got more energy than, less energy than the reactants, so that heat has to be given off. So if delta H is negative, and also think of what's happening in that match, you're getting wood, which is a whole bunch of big molecules being broken up into solid molecules, being broken up into lots of little gaseous molecules. What do you think is happening to the entropy? Is it becoming more disordered or less disordered? More, because I've got lots of little gaseous particles, not even solid, running around now, so it's becoming a lot more disordered. So my entropy is positive. If I have a negative delta H and a positive delta S, then my reaction is definitely going to be spontaneous. It's definitely going to work. Okay, on paper at least anyway. So if you get given a question where you've got an exothermic reaction of, say, a solid going to a gas or something like that, in other words, you know the entropy is positive, the reaction will be spontaneous in all cases. If I have the opposite of that, so I'm going to need energy input, so my system is cooling down, and I'm, say, changing from gaseous to solid, so my entropy is becoming more ordered. So there's a decrease in disorder, so delta S is negative, then I am not going to get a spontaneous reaction under any circumstances. So you can never get, say, a reaction going from, say, gaseous to solid, which is an endothermic reaction. That will not happen. Here's one, though, where it's a little bit different, where I've got a solid. So this is just ice melting. Now, if ice is melting, so I'm getting my particles in a solid form going into a liquid form, am I increasing in disorder or decreasing? Increasing, correct. So I'm increasing in disorder because I've got now more particles that can move around. They're not just vibrating in a fixed sense, they're now moving around. So delta S is positive. Delta H, though, now you've got to think of, do I need energy input into the system, or is heat being given out? In other words, is that an endothermic or an exothermic reaction? So just think of ice melting. Would it be endothermic or would it be exothermic? Do you have to add heat to make it happen, or do you have to take away heat to make it happen? You have to add heat. So it's an endothermic reaction. So now you also know from experience, will ice melt at minus 50 degrees? No. So this reaction can happen if the temperature is correct. And that's where your Gibbs free energy comes in. That T in your equation is for temperature. So what you just simply have to know for the level 3 curriculum is that this reaction is possible depending on the temperature. You don't have to know anymore. So if I've got an endothermic reaction, but I've got a positive entropy change, the reaction is possible at the right temperature. So you know that ice will melt above 0 degrees. So if it's 100 degrees, you know ice will melt. But if it's minus 100, you know ice won't melt. And now the final one here is where I've got water vapor condensing. So it's, in a way, the opposite. So it's lots of gaseous particles forming water. Am I getting more disorder or less disorder in the system? Well, I'm still getting less disorder because my water vapor molecules, they're moving around, you know, they've got lots of entropy, and now they're suddenly coming together. So there's now a bit more order than before. So the entropy, yes, so there's less disorder now. So my entropy is negative, my entropy change. It's because there's less disorder now, it's a negative change. However, what is happening to my heat? Is my reaction exothermic or endothermic? So think of the type of bonds we've got in gaseous particles and compared to water. Now, I'm not talking about the covalent bonds within water, I'm talking actually about the intermolecular forces. If I've got my gas particles zooming around, is there much attraction between them compared to when they come together? Right, they're forming hydrogen bonds. We're now storing up potential energy. So it's actually, now I've gone blank. It's an exothermic reaction. So delta H is negative. Yep. So if we, again now we've got less entropy, but we've got lots of heat being released. So it's again one of those things, you know, water vapor, will it condense at 150 degrees? So I know you're typing there. No, it won't. The temperature is too high. So again, depending on the temperature is whether this reaction is going to work. But you know that water vapor can condense at, say, 50 degrees or 0 degrees, so a lower temperature. So this again, when I have these two symbols, delta H is negative and delta S is negative, the reaction could happen at the right temperature. Now, back to this first one, this, as I say, will happen in all cases, systems and surroundings, it's going to happen. This second one, it's never going to happen. These two will happen if the temperature is correct, and when you argue in the exam paper, when you're trying to justify, remember to explain, okay, this is what's happening in the system, and now you talk about the surroundings. So with your water vapor condensing, you've got to talk about the heat being given out, because it's an exothermic reaction, it's a heat being given out to the other gas particles, and so there's going to be more entropy in the surroundings, and so on. Right, you are typing there. Yes, an air conditioner, well, an air conditioner, you're actually adding energy all the time. So an air conditioner, you're inputting energy all the time, because it won't just work by itself. So it's not spontaneous in itself. It's a bit like, if you like, that electrochemical and electrolytic cell. You've got to make that energy happen, by that reaction happen. Does that make sense? Okay. Okay, so what I'm going to do here is look at, say, an exam question that came up last year, where you've got to explain entropy and enthalpy. So what I've done there is I've highlighted the key points. Whenever you answer an exam, underline or highlight the key points and then talk about them. So state the obvious and then your deduction from that obvious. So the important thing, the first sentence is just simply an introduction to give a context. So the next sentence is the important bit. You're dissolving something. So immediately you have to start thinking, if I'm dissolving, what's happening to my entropy? Because you can see in that very final statement, you've got to talk about entropy. So am I getting an increase in entropy or a decrease? Right, my entropy is increasing. And you've got to then explain why. So you're having more particles. We're going from one particle in the solid to two particles that are spread out. So explain, state that obvious. Then you've got to, I've highlighted the word spontaneous, because remember, for a reaction to be spontaneous, delta S overall has to be positive. So somewhere in your answer you must state that and explain it. And then you're also told it's endothermic. So you've got to relate to that. And then of course you've got to explain. So a one-word answer is not going to cut it. So key points is basically say you've recognized that it's endothermic. So you say it's an endothermic reaction, so delta H is positive. And you could then also say heat has to be added into the system. Okay. Another statement, dissolving, show you've understood it. So you can say you're changing from a solid to a solution, so my delta S is positive because there's more particles present in solution. Okay, and so there's more disorder. So spell out every point. And then remember that statement I said you always have to make in these type of answers. Delta S must be positive overall for the reaction to be spontaneous. Okay, you could say according to Newton's second law of thermodynamics if you wanted to. And then this is the explanation part. So where you're comparing the surroundings and the system. So we're talking about the decreasing disorder and the surroundings due to the drop in temperature. So remember, we're sucking in energy from the outside because we've got an endothermic reaction. So the outside is losing heat because it's being sucked in. So they're becoming slower, they're moving more slowly now, and so it's going to be less disorder. The kinetic energy is decreasing, they're slowing down. In my system, in my endothermic reaction, it's getting colder from the reaction, but because it's sucking in the energy, I'm going to have more disorder because I'm going from a solid to an aqueous. So, you know, what we spelt out in point number 2. And so what we basically got to say is, obviously the increasing disorder of the system is going to have a greater effect than the decreasing disorder of the surroundings. So that must be stated there somewhere. Any questions on that? No. Okay. So that happened in last year. So we've done enthalpy and entropy. Now the next bit is basically taking the enthalpy and doing a whole lot of calculations relating to heat. And in order to do that, you need to know some definitions and be able to work the definitions. So the first one is the heat of formation. So it's delta H, but notice that little F in there. That F stands for formation. That little 0 over there at the top there, that's actually the standard heat of formation, and it just means it's done under standard conditions. Correct, Andrew, then. Just like you got that E cell naught or that E naught reduction potential, the standard reduction potentials that we did in the 3070 series. It's just the standard temperature of 20 degrees, standard pressure of 1 atmosphere, and so on. Actually, I think the temperature is 25 degrees. It's just slipped my mind. So under standard conditions, this will always happen. And it's the heat energy released or required. It could be positive or negative. But the important bit is this 1 mole of substance. So for instance, if I did the heat of formation of sulfur dioxide, it's got to be from the elements in the standard state. So in other words, at room temperature pretty much and atmospheric pressure, sulfur exists as a solid. We know it's a yellow solid. Oxygen will exist as a gas. So those are the elements in its standard state. And notice it has to be for 1 mole. So when we try and balance this equation, in this case it is already balanced, but it has to be a 1 over there. So with these definitions is the one time when you do have fractions at times, and we'll see that in the next one. A heat of reaction is where a heat is given off for the reaction is written. Oh, sorry, actually it's not this one where you see the fraction, you'll see it later. So the heat of reaction, I haven't underlined anything, there's no red line here, nothing has to be a 1. If my heat of reaction for this is, say, 100 kilojoules, then if I had a 2 in front of here and a 6 there and a 4 there, I've doubled it, then my heat of reaction would be double that. It'll be 200 and so on. Or if I halved this, my heat of reaction would then be 50. So the heat of the delta RH is always for the reaction as written. Okay, so you don't have to worry about 1s. That's just the way it is. Now the heat of combustion, this is where you see a half, because it's for 1 mole of substance. So there it had to be in the products for the heat of formation. For this one, it has to be the reactant. So the reactant being burnt with oxygen, and there must be a 1 in front of that. Now normally, if you looked at the equation, you'd say, oh, you can't have fractions, you've got to multiply everything through by 2, so you get 2 plus 9.5 is, I've gone blank, 17 plus 12, and then it's 12 CO2 and 14 H2O. But we can't have a 2 in front of that C6H14. It has to be a 1. So we do use fractions in this case. And then 3 more definitions. Well, I've actually only given 2 here. The one is the heat of fusion, and I mentioned this because there's a lot of confusion between formation and fusion, just because they both start with F. Remember, the heat of formation is to form a substance from its elements. This is just going from a solid to a liquid. I know fusion makes it sound as though it's fusing together, so it should be a liquid to solid. Just think of that and make sure, flip it around. It's a solid to a liquid. So that's the heat of fusion, and again, it's one molecule, or sorry, 1 mole being changed. In this case, though, it's easy to balance because it's always 1:1, because it's just changing state. And the same thing for vaporization. You'll have 1 water molecule liquid going to 1 gaseous. The other one that I didn't write down was actually the sublimation, when it's going from solid to gaseous. Then it's delta sub H0. Okay, now one point, so I'm just going to digress a little bit. Remember what we did in the 304.2 on intermolecular forces, and we used melting points or boiling points, and you had to discuss which ones had stronger intermolecular forces. They can also use the delta H fusion and delta H vaporization for this, because what are you breaking to go from solid to liquid? So to see you typing, you're breaking the intermolecular forces. So it's another way to ask the same thing about the strength of the intermolecular forces. When you're going from solid to liquid, you're only breaking a few of those particles. Not particles, you're not breaking particles. You're only breaking a few of those intermolecular forces. You just want to break some of them to just let them separate. The water molecules are still really close together, so there'll still be a lot of attractive forces, but there won't be as many. So in fusion, you only break some. In vaporization, you have to separate that, and it's really important that you state that to form a gas, you have to separate the molecules. So you have to break all, or just about nearly all, of those intermolecular forces. And because we're breaking more intermolecular forces, a vaporization heat is always going to have more energy than a fusion heat. Okay, so if this was, say, 50 for this one, this can never be less than 50. It'll always be more than 50, because you're breaking more bonds. Okay, so here's just, as I say, it's a bit of a sidetrack, going back to what we did before. But here where they use the delta H vap and delta H fusion, and you can see it's talking about the attractive forces and so on. So remember, same thing as what we did before, talk about all 3 different types of intermolecular forces: the temporary dipole, the permanent dipole, forces of attraction, and the hydrogen bonding. And then, of course, remember, in ice, those molecules are really fixed in position by the hydrogen bonds. That's why ice is actually expanded, because they're really fixed in position. And of course, when you melt, you're breaking some of the H bonds. Before I go further, do you notice that I have used abbreviations there, like IMF and H bonds? You can do that in the exam, but only after you have explained what that abbreviation meant. So can you see my first statement? I said state all 3 types of intermolecular forces, and then I put IMF in brackets. Yeah, if you like. Although, yes, all the 3 significant figures, you don't have to explain that. You just simply have to write it to 3 significant figures. But here I can't just say state all 3 types of IMF, because a teacher could turn around and say, are you talking about the International Monetary Fund? Okay, you have to say what you mean by your abbreviation. And the same thing with H bonds. So you have to say what you mean by H bonds. So my second point, I said, in ice, the main IMF, because I have already explained what IMF is hydrogen bonding. And then I put in brackets H bonds. So now in the third statement, I can say what H bonds are. So on melting, only some of the H bonds need to be broken. But if I vaporize, all of them have to be broken. And so because all of them have to be broken, I need more energy, and so the delta vap is bigger than the delta fusion. Okay, so that's a sort of question. Here's another one. And so like in the past they would have given you boiling points, but now they just give it to you as vaporization. Remember, when they give you molar mass, immediately think of temporary dipole forces of attraction, because temporary dipole forces of attraction are affected by mass. So again, your key points, talk about those temporary dipole forces of attraction, and you will say it's a bigger molar mass, so these greater number of electrons, so stronger, and blah 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 blah. And then of course you've got to talk about all the different types. So talk about the permanent dipole forces of attraction and recognize that both of them are polar. Recognize that the aminomethane or methylamine has got hydrogen bonds and it's a strong bond, but say that the delta H vap is similar because the strong H bonds are compensated for by the much stronger temporary dipoles in the chloromethane. So does that make sense? It's sort of revising what we did quite some time back, where we looked at each individual one. Okay, right, so okay, I can see you typing. Yeah. Now let's get on to the calorimetry, because you will get a calorimetry question, pretty much guaranteed. There's two types. There's what we call the coffee cup one, that's the one on the left, and that's the experiment you do at home with those socks or polystyrene cups if you have them. And that is done at constant pressure because it's open to the atmosphere. Like, we don't even put a stopper on top, which isn't the best thing, but that's constant pressure. The other one that's shown on the right is what we call a bomb calorimeter, and that's constant volume. Correct, because there it's happening inside that volume. It's a fixed piece of metal. The volume doesn't change, but as this substance is burning and giving off gases, it's obviously increasing the pressure. So it's not constant pressure, but it is constant volume. Now before we go on, I want you just to think of what is losing energy and what is gaining energy. So look at this one on the right here. Sorry, why is it not? I'm trying to show my, there it is. So look at this bomb calorimeter. I'm burning something in oxygen. So just think of where, what's the energy doing? Where is it going? It's transferred to the surroundings, correct. It's transferred into that water. So there's a fixed amount of water in here. So it's water that's been weighed out. It's a fixed amount. And any heat that's given off by the reaction is being taken up by the water. So it's being absorbed by the water. So if the calorimeter is increasing in energy, or increasing in heat, the reaction must be decreasing in heat because it's being given off. So I'm going to use that because we're going to have to explain a sign just now, a positive, negative sign. So as I said, you don't have to really know about constant pressure or constant volume, but that's just to show that there are those two different types. So let's work through some calorimetry equations and calculations. First of all, you do need to know what we mean by specific heat capacity, because that's why we use water. Water, we know, and it's been measured, absorbs a certain amount of energy per gram of water, and that's what's called a specific heat capacity when the temperature is raised by 1 degree. So it's given for pure water, it's 4.18 joules per gram per degree centigrade. So what we're saying, if I have 1 gram of water, so 1 milliliter of water, to raise the temperature of that 1 milliliter by 1 degree, so if, in other words, if I want to change it from 20 degrees centigrade to 21 degrees centigrade, I've got to add in 4.18 joules of energy. So I've got to heat it by that amount. So that's what we mean by specific heat capacity. And every substance has got its own specific heat capacity. Water is very high. Most metals are 0 point something or the other. They're very low. Okay. So the heat transferred in a reaction we can work out by saying, okay, what is the heat being absorbed by the water? So that's where that mass of water comes from. The 4.18 is the specific heat capacity of water. And of course, we need to know the temperature change. Then we divide the whole thing by 1,000 to change my units from joules, that's given in the specific heat capacity, to kilojoules. So if you like shorter equations, I mean, there I tried to just explain what was being meant. You could say Q is equal to MC delta T. Delta T is the temperature change. Delta always means change. Okay, so T is temperature. C is the specific heat capacity. And you don't have to learn that one off by heart. You will be given it for water. After you've done lots of them, you'll know it off by heart anyway, but you will be given it in the exam. And M is the mass of the water. It can be the mass of the solution if you're only given the solution, but then you'll be told that, you know, the density is the same, or the specific heat capacity for the solution is the same. So we'll look at some examples on that. Now remember what I said, what's happening to the energy being transferred, you know, in or out. If I'm getting a temperature rise in the water, okay, it means that the delta T is going up, okay, it's positive, and therefore the calorimeter is increasing energy. So temperature rise means more energy, the water is getting hotter. What therefore that means is that the reaction is losing that energy to the calorimeter. So, and this is where we get the negative from a exothermic reaction. If the calorimeter is gaining in energy, the reaction must have lost it to the calorimeter, so it'll be a negative. I don't know if I explained that very well, but you'll see it now when we do an example. So here's an example, okay? Whenever you see a whole mass of numbers like this, I really, really strongly recommend you highlight the key points, okay? Underline them, use a highlighter, whatever you've got. It just makes something stand out from all those hundreds of words that are out there. So you know you're given a mass there of KOH. You're given a mass of water. So you've been given two masses, okay? You've been given two temperatures, which is fine because you want a temperature change, so the delta T we were talking about. And I've also highlighted what we're aiming for. At the end of this calculation, we must have answered delta H solution equals something in kilojoules per mole. We must finish with that. And then we are told the calorimeter doesn't really absorb much, which means all I have to worry about is the water in the calorimeter. I don't have to think of the metal part of the calorimeter absorbing any little bit. And we've said that the specific heat capacity of the solution is the same as that of pure water. So we're assuming that. So when I start this calculation, I strongly recommend you write those values down. Because especially if you don't know where to start. Like you think, oh, I've got two masses there. I've got temperatures there. Where do I start? If you list things, it will help you trigger your memory on something. So for instance, if you see 4.18 joules per gram per centigrade, hopefully you'll think of the calorimeter equation. Q is equal to MC delta T. So hopefully that will be a trigger whenever you see this particular value. If you see M and a big capital M, actually that's not been given, I actually put that in. Whenever I have a mass, I always think of the molar mass. It's always good to have the molar mass because that way you can work out the moles. Remember, I wanted it in moles I want it in kilojoules per mole. This doesn't give it to me as per moles. It only gives me as joules, not joules per mole. So I need to have mole somewhere, which is why I added that molar mass. The mass, and I should have actually said mass water here. That's that mass of the water in the calorimeter. That's what we use in our equation. So let's get going. First of all, this, remember, is the heat being absorbed by the calorimeter. So that's what that Q is. So MC delta T, the mass of the water, the specific heat capacity, and there's my temperature change. And what I'm trying to show here is if I cancel out my units, can you see I'm only left with the joules? Okay, so if you've forgotten the equation, say you've had a blank moment, you don't know what the equation is, do I multiply, do I divide, what is it, MC divided by delta T, is it C divided by M, you know, you get all muddled. Use your units, and if your units cancel out correctly, because you know heat is in joules, kilojoules, but it has to be joules. So if you get an answer of joules and not joules to the -1, you know that you're on the right track. Okay, so I've got it there in joules, but remember the question did ask for kilojoules per mole, so we have to convert joules to kilojoules. So I've divided by the 1,000 to get to kilojoules. Now remember, the Q calorimeter is always the opposite to the Q reaction. So if I get a positive value of 4.89, my reaction is exothermic, it's negative 4.89. So that's what I was trying to show in that previous slide. Is that clear now about why we changed the sign? Yep. Okay. So you can see I've got my answer to kilojoules, but I can't finish there because I was told it's the delta H in kilojoules per mole. So I need to now convert. And of course, if it's per mole, it means I have to divide by moles. Now, were we given moles anywhere in that list? No, but I can work it out by using N is equal to small m over big M, mass over molar mass. So those two values are now used. Remember, you may not be given the molar mass. You're always given a periodic table, so you can work it out from there. So K is 39, O is 16, H is 1, well, 39.1 for K. So that gives you 56.1. And so you work out the number of moles. So take the kilojoules divided by the number of moles, and there you get the delta H solution as moles, kilojoules per mole. Easy peasy. It's only difficult because it's in two steps. You've got to think of one equation, and then you've got to think of the other equation. So listing the things really helps, especially if you group them, mass and molar mass together, and so on. Here's another one. Now, I've treated this one slightly differently, where I've not highlighted, and I've just written down a whole lot of values. Could you get going on this calculation, just looking at those list of values? Or is this actually making it really difficult? Okay, so you're not volunteering an opinion. What I'm trying to highlight here is when you write down your list, give a context. Don't just write down numbers, because if anything, it's going to make you even more muddled. So list. Now, do you notice I don't just say M? Yes, yeah. Don't just say M. Say M hexane, because M could be, did you mean the water? Did you mean the hexane? Did you mean the what? Okay, so if you give a context, I'm talking about M hexane or M water, then it's much clearer. And you'll find another one where we've got two different things, HCl and ammonia. So spell it out what you're talking about. So I'm putting in units, because remember, if we use units, we can cancel the units out to make sure we've got the right equation in the first place. We haven't made a silly mistake there. And always work out what you're going for. So I'm actually trying to work out the heat of combustion there. Remember, delta HC is the heat of combustion. So now we just go for it. Again, though, listing it hopefully will make you think of other equations. So the Q is equal to MC delta T, as well as the N is equal to small m over big M. And let's go for it. I've got the units highlighted because just to make them fit in that tiny space, I've taken the units out there. You try and always put your units in if possible. So do you notice I've first sort of put the equation in and then I've substituted? If you don't put the equation, if you substitute straight away and you've made a silly error, it's very hard for the teacher to work out what you've done because all they see is a mass of figures. And if your figures are wrong, they can't work out what you've done, and then they give up and give you 0. Okay, whereas if you've put down the equation and you substitute, they can say, oh, I can see you got that one right, you got that one right, but you made a silly transcription error there, and you could still perhaps possibly get achieved rather than, 0 for that bit. Okay, so it's the same sort of thing. You get your kilojoules, but you need kilojoules per mole, so you have to divide by the number of moles. And that's what that 0.4 divided by 86 is. It's the mass divided by molar mass. Sorry, I've condensed the calculation there a bit. Right, one more, and here I've done it out as the first one we did. Highlight all those bits because there are lots of bits. Okay, work out what you're going for. Then write down and give context, give units, because now do you notice I've got hydrochloric acid there and ammonia. So you don't want to muddle up your volumes and so on. In this case, you were given the same volumes and the same concentrations, so it's not so bad. But if you were given different volumes or different concentrations, you want to make sure you've got it right. Okay, that I'm mixing it up. And notice that I've got a mass for the mixture, okay, but you're told that the aqueous ammonium chloride, which is that mixture, is 4.18. So we're assuming it to be like water. So we know that 50 grams is that when I go MC delta T, that's that M. So, okay, there we've just got, remember to work out the moles, because we need per mole. So if we've got milliliters and moles per liter, hopefully you're thinking of C is equal to N over V. Now you do need a mole ratio, just to work out your final concentration of ammonium chloride. So there it's easy, it's all 1:1. 1 HCl reacts with 1 ammonia, gives me 1 ammonium chloride. Now I've done that sort of, it's perhaps quite difficult to read because it's all in one line, but can you see I've written the equation first, then I've substituted, and then I've converted joules to kilojoules. So you can see my M was 50, my C is 4.18, my delta T is the 6.5, and then I've got the joules, and then I converted to kilojoules. Then I have to show, so for excellence, if you didn't put this line in, if you had just sort of gone ahead, the teacher wouldn't know that you've seen that the number of moles of ammonium chloride is 1, or whatever it happens to be. So if you were to say working with HCl, you need to know that you're working with ammonium chloride. And the number of moles of ammonium chloride is going to be the same as the number of moles of HCl you had in the first place. So that's what that line is for. It's showing you understanding what's happening. So I'm first working out, I've taken my delta H, the heat given off in the reaction, and I remember I've put that negative sign in, because remember the calorimeter, if the calorimeter is positive, then the reaction will be negative. Okay? And if, of course, the calorimeter was negative, then the reaction would be positive. And so that's where that minus comes in, and I've worked out the moles. Sorry, I didn't show it here because it was getting a little bit, hang on, it wasn't that third line. So it's 250 moles, and I've used the ratio, and then I have to give the final statement. Teachers like it that you have the final statement for excellence. I have once seen it where they specified you had to have that down. So it's a good idea to get into that habit. Right, there's not much time left, but I do want to do one more thing, and that's heating curves. You can, and this also happened last year, you got this in a question, last year's exam. Basically, if we're going from a solid, and then we're melting that solid, then we've got a liquid, and then we converting that liquid into a gas, and then I've got a gas. So that's what I'm trying to show here. I actually got it from a website, and these were actually GIFs, so you could see that vibrating here, you could see it starting to come apart, you could see these moving around, then it's getting a little bit more hectic here, and then they're dashing around like crazy as a gas. So we're trying to see there's this increase in kinetic energy, and that's why there's this slope going up. As I'm adding heat, the molecules are taking up that heat you've added and converting it into kinetic energy. They're moving around a lot faster. So in the solid, as you're adding heat, they're vibrating more and more and more and more and more and more and more. Okay? Until they get to where this level thing happens over here. It's level because although we keep on adding heat, so it's not as though we've stopped heating, we're adding heat. But where do you think that heat's going? Why is the temperature not rising? Because the temperature is a function of kinetic energy. So we're saying the kinetic energy is the same all the way through that bit over there. What is happening to that heat? We can't make the heat disappear. So it's got to go somewhere. It's being absorbed. It's being absorbed by the solid, and that energy is being used to break the bonds. So won't be breaking all of them because it's just a fusion. So it'll be breaking some of the bonds. So although we're showing it fairly separated here, there's still some forces of attraction between these particles. They should actually be a lot closer together in this liquid. It's not actually a very good diagram. So they're a lot closer together here. So while we're breaking the bonds, all that energy is being transferred into breaking the bonds. When enough bonds have been broken, the liquid particles can move around now, so they're increasing in kinetic energy. And then we get to this bit here where they're breaking more of the bonds, in fact all of them. So all of the bonds are being broken, so all the added heat is being to break every single intermolecular bond, or force of attraction. And then of course the gas particles, you can heat and heat and heat gases, and they'll just whiz around faster and faster and faster, getting more and more kinetic energy. So that's how the heating curve works. It's temperature going one way and the heat going the other way. Now, do you notice this one's water? Where does this line correspond to? What is this? I know it's zero, but what do we know about zero in relation to water? It's a phase change. That is the melting point for water. So when we have that flat line, as we add heat, that's when there's a change in phase and it's the melting point. Or it could be, and you'll see over here, 100 degrees, the boiling point. I mean, we know that at any time particles can go into the gaseous phase, but that's just because as they're moving around, they could be one particular particle could be whizzing around, it's collided, it's been gaining a lot of energy during that collision, and it's enough to make it break free. But it's only got a certain amount of energy, and it might just come back and form the water again. So the boiling point is when all the bonds can be broken, all the intermolecular forces bonds, not the covalent bonds, and you can separate the particles. So that's what I've said. The heating causes the particles to gain kinetic energy in the interim phase, but when we're at the boiling point or the melting point, the heat is being used to break the intermolecular forces. And finally, finishing off with last year's exam in the last minute. So this is what came up in last year. It was one of your first labs. Okay, right. This is fun. So basically, what we have to explain is this difference between A to B, B to C, C to D. And really what we're saying, as we're going from A to B, the added energy, this is in time and minutes, but remember we're heating up this this, is it water? And it's ammonia. So we're heating up this container of ammonia. So over time, what's happening to that heat that we're adding? So during just 2 3/4 minutes to, I'm trying to find this, 2 3/4 minutes to around about 3 3/4 minutes, that added energy is being just simply taken up as kinetic energy. The particles are moving around faster, and so we have a temperature increase. So you can see up here's temperature, it's going from minus 80 to sort of minus 40 or 30 something. Okay, then B to C, that's when you're breaking those. Now show that you know what you're talking about. It's hydrogen bonds and ammonia is the main bond. So these hydrogen bonds being broken. So I can't see my cursor. Hydrogen bonds there. So that because all the energy has been going to break the bonds, there's no change in kinetic energy. And that is therefore the boiling point. And then now we've got gases. So show you know that between C and D is a gas. Okay, so between C and D is a gas. So as I'm adding energy, they're changing. They're just simply increasing in kinetic energy. So those are the 3 important points you have to say. Right, so just over an hour. Any questions? Okay, right, so I'm glad you got no questions. Remember, you can email at any time a question if you've, stuck on something and you want me to explain it. I mean, you can ask me on the day, but if you email me beforehand, I can sort of make it a nice PowerPoint sort of thing, so it's neat instead of my scrawl. Okay, so all the best, and see you next week. Right.